In this video and the next, we're going to be discussing the two types of special right triangles. Special right triangles typically come up in a geometry course as your first introduction to them, and then are later an important part of a trigonometry course, especially in the context of setting up what's called the unit circle. Here we're going to be discussing the special right triangles, where they come from. They come from two of our regular polygons, and we're going to be discussing the ratios that exist within those triangles. So with that in mind, the first of our special right triangles comes from a square. And I've got a square ABCD drawn here, as you can see. In that square, we want to draw in one of its diagonals, effectively producing two congruent triangles. Now, there's special relationships that exist between these two triangles. First of all, we know they're congruent to each other, and we know that's true because of side angle side. But aside from that, we also know that these two right triangles, since they have one right angle each, also are isosceles triangles based on the fact that their legs are congruent. So with that in mind, if a triangle is isosceles, if it has two congruent sides, then it must also have two congruent angles, specifically the angles that are opposite those two congruent sides. So here, if we consider this triangle ABC for a moment, in that triangle, this side would be opposite the angle BCA, and this leg would be opposite angle BAC, which makes those two angles congruent to each other. Now, if we go back to what we know about the Triangle Sum Theorem, we know that the three angle measures in any triangle have to total 180 degrees. So what we have in this case, we have a right angle that's going to take up 90 of those 180 degrees, which means the other 90 degrees must be evenly split between these two angles, making each of these angles measure 45 degrees. And this is your first type of special right triangle, what's called the 45-45-90 triangle. Usually when people talk about this particular type of triangle, we're referring to it by its angles. And it's typical to say 45-45-90, even though we have the degree symbols written in here. It's not common to state 45 degree, 45 degree, 90 degree. It's not wrong, it's just not typical. So a 45-45-90 triangle comes from half of a square, what we get whenever we divide that square in half on one of its diagonals. Now let's talk about the lengths of the sides of this particular triangle, and for the moment we're going to ignore this other triangle ADC, focusing our attention on ABC instead. So let's say that this triangle has side length x. We know it's isosceles, so both of the legs have to be congruent. And we want to determine from that the length of that hypotenuse, AC. In which case, we'd look at the Pythagorean Theorem. So here, leg squared plus leg squared becomes x squared plus x squared, would have to be the length of the hypotenuse, AC, squared. Okay, so combining like terms on the left, x squared plus x squared becomes 2x squared equals AC squared. So we want the length of the hypotenuse. We want to know what is the length of segment AC. Well, in this equation that we now have, to get AC by itself means that we need to get rid of this squared. And the way that we do that is by taking the square root of both sides. So if we apply the square root on both the left and the right, what we're going to be left with is the square root of 2, the square root of x squared. Remember, the square root and the squared are going to cancel each other out. So that's the square root of 2 times x. And then on the right side, we're left with AC. Now, it's more common with radicals to write the whole number or coefficient part in the front and the radical behind it. It is multiplication after all, so that commutative property allows us to switch the position of those two quantities or factors, which means in this case the length of the diagonal would be x times the square root of 2. And that sets up the relationship for the 45-45-90 triangle. Now, there are a few different ways that some books or websites or videos will talk about the relationship between those lengths. One way is going to be with variables in place, x, and x root 2. Some are going to write that in ratio form, x to x to x root 2, where we're understanding that each of the individual x's represent legs, and that x root 2 represents the hypotenuse in the triangle. Other books are going to say, well, what if we let the length of x, the side, be 1? In which case, if x is 1, we'd say 1 for each leg. And here we'd take x, which is 1, times the square root of 2 and get the square root of 2. So effectively what we're looking at there is a right triangle that's isosceles with legs length 1 and hypotenuse with a length of root 2. Other books are going to talk about it in terms of equations. We could say that in a 45, 45, 90 triangle, the length of the leg times the square root of 2 is equal to the length of the hypotenuse. And it's really just a matter of opinion as to which one you're more comfortable with, as to which one you're going to use. In some instances, it may be very simple to go with either of these first two, with the x root 2 or the 1 root 2. In other cases, it may be more simple to think about it in terms of an equation and solving something from there. In this video, we're not going to really be discussing how we use these. We're going to talk about that in the next video. But ultimately, the format or the structure of a 45, 45, 90 triangle is that the legs have to be congruent and the length of the hypotenuse has to be the length of the leg times the square root of 2. It's also important to remember that the 45, 45, 90 triangle is half of a square. If you can rely on that, if you can go back to the fact that it's half of a square, then you eliminate the need to constantly remember all of this. I'm not saying it's not important to remember these. It is, but you can always go back to what you know about a square and develop it from there if it's forgotten. So a 45, 45, 90 triangle, half of a square, obtained by drawing one of its diagonals, and the ratio of the sides is the legs are congruent, and the length of the hypotenuse is the length of the leg times the square root of 2.